Einstein's special theory of relativity combines space and time into one dynamic unified entity, spacetime. But if time is connected to space, can the universe be anything but deterministic? And does that mean that the future is predestined? In the last episode, we saw that we could think of the unified spacetime in terms of the block universe, an atemporal entity that sort of just exists. In a block universe of Einstein's relativity, there's no way to cleanly define the present, and so no way to cleanly separate the future from the past. The notion of the present is relative. To us, it looks like a particular slice through the block universe. But different observers will slice the block at different angles that depend on their velocities. That means that for every observer it's possible to imagine another observer who lives in their definition of the present, but for whom your future is already the past, or for whom your past is their future. But how does this give us a deterministic universe? Well, if we accept a unique reality for those other observers in our present, and we accept that their perception of the present is as valid as ours, then all of the future is defined. That seems to support the philosophical stance of eternalism, the idea that all space and time exist from a sort of God's eye view from outside of both space and time. And it suggests a deterministic universe where every slice through the block universe is completely determined by every other slice, either behind it or ahead of it. They are connected by the unalterable laws of physics. So here's the big question. Given that relativity is definitely a good description of space and time, what would it take for our future to remain undefined? It seems we have two options. Either the entire block universe is defined past, present, and future, or everything outside our past light cone is undefined, including other observers and the room around you in what you would normally think of as the present, and the only aspect of the present that exists is a vanishingly small patch of space-time around your own brain. In order to even try addressing which of these options is right, we need to take into account something we've totally ignored so far. Where relativity is the key to understanding the universe of the large and the very fast, we also need to understand the universe of the very tiny. We need to see what quantum mechanics says about determinism, and how it plays with relativity and the block universe. According to quantum mechanics, physical systems, parts of the universe, evolve as wave functions, not as well-defined reality, but rather as distributions of probability that describe all possible states that chunk of the universe could be in if it were to be observed. The wave function can be thought of as a state in which all physically possible realities intermingle. Countless extremely precise and frequently replicated experiments tell us that the universe really does exist in this indeterminate state in certain circumstances. The wave function is real. The big question is what causes the transition from this world of quantum indeterminacy to the solid singular reality of the macroscopic world. We've talked about this profound weirdness in many episodes, including how to interpret it. Now, exploring those interpretations again may help us understand the state of the universe beyond our immediate selves and the immediate moment. One of the earliest and still most accepted interpretations of all this weirdness is the so-called Copenhagen interpretation, which states that a quantum system is literally in a state of undefinedness until observed, at which point the wave function collapses into a defined state. All particles take on defined properties, and one actual reality is chosen from the many possible ones, at least as far as the Heisenberg uncertainty principle allows. The Copenhagen interpretation gives us a non-deterministic universe. The wave function evolves in a precise way, perfectly defined by the equations of quantum mechanics, but at the moment of measurement, a single reality is randomly selected from the distribution of possible realities. The dice are thrown when the wave function collapses. That means it's fundamentally impossible to predict the state of a system after observation. Another popular interpretation of quantum mechanics is the many-worlds interpretation, which simply states that the wave function never collapses. Instead, all possible states of the quantum system continue to exist. Rather than choosing one reality out of many, when we observe a quantum system, we sort of just become part of one of the realities and lose track of the others. The many worlds interpretation gives us a deterministic universe, or rather a deterministic multiverse. The wave function never collapses, it evolves deterministically forever. The illusion of randomness is that we find ourselves in the one branch of the wave function corresponding to the reality we perceive. But we aren't randomly placed in that branch, we just are a part of that branch. So how do these interpretations connect with what relativity tells us about past, future, and present? Let's start with Copenhagen. It's tempting to equate everything outside our past light cone with the unobserved wave function. You can imagine that light cone sort of just ploughing through the undefined universal wave function, collapsing it as it goes, or at least the parts of that wave function for which signals actually reach our awareness. That leaves your future light cone undefined, a non-deterministic void with room for your non-determined choices. But now, let's say we believe that other observers in the universe can also collapse the same universal wave function with their observations. Well, no problem so far. You can imagine this fleet of observers collapsing the universe all the way up to what you perceive as the present. Your future is intact. But wait, we saw last episode that your impression of the present is relative. A fast-moving observer defines the present very differently to you. In fact, any part of spacetime not in your future light cone is potentially the past for another observer in your present. And that observer can imagine a third observer on their different present for whom your future light cone is in their past light cone, so it should have already been collapsed. The upshot is that with no way to define an absolute definition of the past, and if we believe in other observers, there's no way to keep the wave function of your future from being collapsed before you get there. Now, there are subtleties in this wave function collapse idea. Copenhagen doesn't specify what causes the collapse. It could be observers, as in the von Neumann-Wigner interpretation. That's the hardest to gel with a non-deterministic universe, unless you're the only observer in the universe. More physicists prefer the idea of a non-conscious interaction causing the collapse. In that case, uncollapsed wave functions tend to exist only in microscopic pockets or in very special circumstances. But that doesn't help uncollapse your future. No, the only totally coherent way for a non-deterministic wave function collapse interpretation, like Copenhagen, to give you an uncollapsed future is if you're the only being doing the wave function collapsing. Let's move on to many worlds. This interpretation sits a bit better with the relativity of past, present, and future. Your light cone sweeps through the global wave function, but it doesn't collapse that wave function. Rather, it selects from it. Sometimes the quantum multiverse of many worlds is depicted as this branching tree in which the realities multiply as time progresses. In the block universe picture, it's tempting to depict this as the entire block multiplying with every quantum event, but that's not quite right. A division in the block universe can only propagate as quickly as the result of that quantum event can become known. That can happen at the speed of light, so we can also think of the splitting as proceeding in advancing light cones. Really, what's happening here is that parts of the universe become entangled with each other, correlated at a quantum level. So we have these spreading webs of entanglement. Each such web defines a set of properties of the universe correlated with some prior quantum decision, with an independent web existing for all different possible decisions. Here we're bringing in the concept of decoherence and quantum Darwinism, which we've covered before. Decoherence is an explanation for how the worlds can become separate from each other when you shift from simple systems like an atom to complex systems like a cat. According to the decoherence explanation, the quantum multiverse isn't a cleanly divided set of alternate realities, rather it's a tangled network of alternate sub-realities. Nonetheless, as your light cone moves forward in time, you encounter these entanglement networks and you have to choose between them. Your reality is the particular set of entanglement networks that you interact with, and there are other realities with different networks that contain different versions of you. I should add that the light cone picture isn't ideal here because entanglement can travel faster than light. However, light speed signaling is the surest way to transfer quantum correlations, so this is still a useful picture. So, what does all of this say about determinism and the reality of your past and future? Well, interesting things actually. The evolution of the wave function is deterministic. That means all future branching of the wave function of your present, by which I mean the entanglement network that you currently belong to, is predefined. What isn't defined is your own experience of that future branching. You will be the thread of conscious experience that travels one of those branches. You'll also travel the others, but each version of you will only feel like you traveled one of them. This interpretation, many worlds plus decoherence, perhaps gives us the most concrete notion of an objectively existing present. It's that part of the global weight function that you're connected to via entanglement and that shares your timestamp of now. But the notion of now remains relative. There are still other observers in your slice of reality for whom your now is their past or future. Copenhagen and many worlds aren't the only interpretations of quantum mechanics in town. We should make an honourable mention to de Broglie-Bohm pilot wave theory. This is an entirely deterministic interpretation that doesn't have multiple realities, just a wave function that guides particles in a perfectly determined way, defined by Bohmian mechanics. Of course, we've talked about all of this before. The universe of pilot wave theory is really a block universe. But unfortunately, no one has convincingly figured out how to make Bohmian mechanics work properly with special relativity. So it's a very simple block universe, and it's not a good representation of ours. There are other interpretations that deserve mention, but we're out of time. So, does the future already exist according to quantum theory? The answer depends on your favourite flavour of quantum interpretation. Perhaps we ride the dice of Copenhagen into an unknown future, or surf the splitting quantum multiverse into all futures of which you will become just one. Of course, we still haven't got to why time needs to progress in one direction at all, or how time even arises in the first place. But we'll have plenty more time for time another time on Spacetime. Hey everyone, last week we introduced the idea of the relativity of simultaneity and the block universe and what this might tell us about the reality of the past and future. At least I think it was last week. The whole time thing's very muddled in my head these days. But let's see what you had to say. Anonymous makes some important points. I'll summarise. In Einstein's relativity, the definition of simultaneous events is, well, relative. It depends on relative velocities. So does that mean that the idea of a now slice through the block universe is meaningless? Well, maybe, but two observers can certainly construct a map of events across the universe that they would define as happening simultaneously at a given instant in time, their slice of now, and compare those maps, even though they have to wait until the light reaches them to do so. So the now slice has a precise meaning. What it does not have is the property of clearly and currently existing to the exclusion of other slices in the block universe. And that's where the relativity of simultaneity connects to eternalism. If you can ascribe actual existence to one slice of the block universe, to one observer's definition of the present, then you should ascribe existence to the slice of the present as defined by any potential observer on that first slice. And that fills the block universe, past and future. The alternative seems to be to not ascribe reality to any observer's present. But then what exists? Just the one observer? At any rate, the relativity of simultaneity doesn't prove eternalism, rather it shows that presentism, or the idea of the growing block, interpretations are incoherent. And speaking of presentism, Carl Stanlund raises a point that highlights another objection that I have to the concept. If only the instant exists, what is that instant? Is it a very short stretch of time, like one Planck unit of time? Or is it a truly instantaneous stretch of 0 seconds? As much as physicists hate to talk about consciousness, I think it's relevant to bring up here. Our conscious experience exists. In fact, it's the only thing we can observe directly. But that experience almost certainly is emergent from the action of our neurons, and those neurons take time to fire and communicate across the brain. So something that currently exists, our consciousness, is smeared out over at least 100 milliseconds of time. At least that length of the present should be thought of as real. You might argue that our conscious experience rides the leading edge of the brain's action, emerging in a true instant, synthesizing prior brain activity. But for that to be a true zero-time instant, then it would need to be the instantaneous state of the brain, the momentary spatial configuration of its particles at that instant that gives rise to our conscious experience. So then does a frozen brain just experience the current instant eternally? Most probably not. Rather, consciousness surely requires dynamical processes, a flow of information. That means that at least a short chunk of the block universe has a real current existence, much larger than the Planck time. And if that much time can exist, then why not all of it? Guillermo Marcassani takes issue with my characterization of Einstein as the smartest man in the block universe. Dude, I said block universe, not universes. Rick is the smartest man in the multiverse. Also, I'm pretty sure Einstein was another renegade from the citadel of Ricks. The resemblance can't be a coincidence. And for those uninitiated into Rick and Morty, there are other funny pop culture references in the comments. Drake gives a nice Douglas Adams quote, "Time is an illusion, lunchtime doubly so." Grandpa's Place reminds us of Doctor Who's experience of time as a big ball of wibbly-wobbly timey-wimey stuff. But really, you should also just go and watch Rick and Morty. Think of it as a co-requisite study course to PBS Spacetime. Wubba-lubba-dub-dub.